Officially kick this off and say good afternoon, everyone. For those that don't know me, my name is Sarah Higgy, and I'm the CEO here at the Electrical Association of Philadelphia. Today, I'm joined by my colleague, Matt Dybert, and our presenter, Kyle Kocarek from Schneider Electric. Thank you both for joining us today. Before we get started, a couple of things here that I'd like to mention. Number one, I'd like to give a huge shout out to Tom O'Neill with Schneider. He's our Schneider Electric's territory sales engineer here in our region for both coordinating this session as well as a variety of things for the Electrical Association of Philadelphia. So we really appreciate your support, Tom. You may have also noticed we cannot see you, we cannot hear you. We've done this by design. We are recording today's session, and so this will make sure that there's a great experience for everyone here. But that doesn't mean we don't want your questions. There's the chat feature. You're going to see some messages pop out throughout the course of the presentation. If you'd like, you're welcome to submit a question for the group. You can submit it just to myself or Matt, and we'll field those questions towards the end of the presentation. So now it's my pleasure to formally introduce you all to our speaker, Kyle Kocarek. She is the product manager in Schneider Electric's Power Systems business unit. Kyle's low voltage team is responsible for switchboards, LVMCCs, panel boards, in low voltage draw and flex set in the United States. She is a very impressive individual in terms of her background. Prior to joining Schneider, was the design engineer and product manager at GE Lighting. She holds a BS in mechanical engineering and an MS in engineering management. So guys, this is going to be an excellent presentation. So with that, Kyle, I'm going to kick it over to you. Thank you so much.
Sure. Thanks, Sarah. Hi, everyone. Thanks for joining. Again, my name is Kyle. And like I said at the beginning, I'm based in Cleveland, Ohio, but my team covers our low voltage power systems offer across the US. So today, we're going to talk about arc flash mitigation and specifically protecting or isolating the line side. But I'll give a bit of an intro kind of just on what it is. We'll cruise through that and why it's important. And then we'll dive into line side mitigation. So arc flash hazards are, the top pain point of NFPA 70E. It's not only about safety and protecting workers from hazards and preventing arc flashes from the get-go, but also uptime, or rather you have a lot of downtime if you do have an arc flash event that hurts productivity, can result in lawsuits and a whole other kind of host of headaches. So we'll get into what can we do about this and be preventative that isn't just PPE, which is not a solution. So super quick, arc flash, it can happen at any kind of regardless of voltage. Mostly we measure it here in terms of calories per centimeter squared, the incident energy. And you can see the chart on the right, a couple of stats about arc flash, but you can have pressure blasts that could knock someone over across the room. You'll have shrapnel or molten metal from this blast, heat, high heat, and also rapid expansion of gases when they heat up. That can be extremely dangerous. So not anything you want to be near, and certainly something that we want to prevent rather than just contain or have PPE on. So it's all about engineering system solutions to prevent this from happening in the first place. Again, arc flash is a real risk. We only have statistics from events that are reported, but there are several incidents a day in the US. And again, it's a huge safety hazard, but it's also a big costly expense that results in downtime and from disrupting your operations and kind of the fallout from that. So this is something that hopefully I'm guessing that your customers have at the top of mind today. And I think we've been getting a lot better in the recent years that, this is something that people are addressing and paying attention to. So again, last slide before we kind of jump into it, arc flash mitigation is really complex. Like one webinar isn't going to solve it. One brochure on the newest, technology isn't going to solve it. You have things like overcurrent protection devices, like a breaker as your first line of defense. Your incident energy there is proportional to your fault clearing time. This is dependent on characteristics and settings of your overcurrent protection device, and it may depend on your equipment construction and also your location of your CTs. In some cases, it's okay to have this breaker inside of the gear, but in others, it might need to be remote or in another enclosure. In some cases, finding something to trip is the challenge, and we'll get into that. Again, you can also address this with fault detection, like a breaker, a fuse, or a relay. And then there's a whole other, this slide is meant to be a little bit chaotic and overwhelming because there's not just one way to address this, and you've kind of got to attack it from all angles, and there's not a one like fits all solution. You really need to do a study and really understand it, which my caution there too is it is complex. So, a coordination study or that alone might not really address the total picture. So Schneider has a lot of really smart people that can help with this and make sure that we have a solution for, to address this, because safety is a huge issue. So there's a lot of options. It's very complex. It depends on what you're seeing and what your lineup is. But we'll jump into line side isolation going forward. So Matt, maybe we'll do a poll here, that first one. So it should pop up, and I see it too. Are you seeing sites with incident energy requirements? And then if so, what's their target incident energy or cals per centimeter squared? So we'll give this a minute just to, and again, none of these polls are like right or wrong answer. It's really just, I'm curious kind of on the landscape out there and what you guys are seeing in a day-to-day. Right now, it's pretty evenly split in terms of all three. So some of you are saying no, like your customers aren't talking about incident energy targets. Some say yeah, some are answering that middle one, yes, less than 8 cals per centimeter squared. And others, yes, it's on their radar, but they might not have a target incident energy level or calories per centimeter squared target. It is, yeah. Pretty dead even there. Interesting. Matt, do I just X out of the poll? Maybe I'll just collapse that and carry on. Okay, so jumping in kind of to line side arc flash isolation. I should have grabbed the booklet from my closet, but this is just a couple of screenshots from NFPA 70E. They rev their significant changes every 3 years. So this isn't the most recent one, but just before that, this is the 2021 significant changes rev. You can see top right is like the cover page of the booklet. And towards the end, I think it's second to last page in Annex O, they added this new section, Annex O.2.35, where they call out a new means to reduce incident energy by isolating energy on the line side of a breaker or a switch. And then they say this is extremely useful where line side propagation of an arcing fault will increase the incident energy released at an event. There's a picture of our P-frame or 1200 amp arc block line side isolation technology, and there it is inside of Model 6. That one's a bottom fed. We can also do top fed here. But so this isn't just Schneider saying like, hey, we have this technology, it's great. This is NFPA 70E recognizing, and I met the guy who leads this committee at a NECA safety event a couple of years ago out in Phoenix, I think. And he actually works closely with Eaton to the point that some of our codes and standards guys said like, maybe he won't talk to you. I don't want to say that. He was a very nice man, but he came up and we talked and he said, I listened, and he said, I don't want to be cliche or cheesy, but I listened to a webinar because I said, how did this get in here? And I'm sure our codes and standards guys worked with the committee too, but he said, this is game changing. This is something that doesn't exist before, where you can protect the line side of equipment in instances where maybe you can't fit upstream, like at a utility entrance or a unit substation entrance. So this is in there because it really is making a difference in arc flash protection on the line side. So it's in this annex. That doesn't mean it's code yet. I don't want to confuse the two, but I still think this is something of significance. So I'll jump over to the video real quick just to talk you through. I'm going to kind of go step by step. There's not sound, it's just going to be my voice. So it's going to show 2 arc flash events, one without any arc flash mitigation and one with arc block, and picture or video is worth 1,000 words. So that's an arc flash event without anything in a motor control center. That's at our Cedar Rapids lab. That's probably maybe 20 or 30 cals. You can see it's a pretty significant. I wouldn't want to be standing anywhere in that room. Now it's going to play the same what you just saw on the left, now with arc block in our Model 6 MCC on the right. It's apples to apples, same exact available fault current, and you can see the difference. It'll play it twice, and we freeze it, we capture the moment. So again, same thing you saw, and then same available short circuit. It'll play one more and I'll pause it. Arc block, again, this is a bottom fed before. So again, probably 20 to 30 cals per centimeter squared on the left. And then on the right, arc block is UL verified per their recommended practice 2986. UL verified to have the incident energy exposure be less than 1.2 calories per centimeter squared. And so that's what you can see there. I probably have a slide on it, but UL recommended practice 2986, they take a bunch of calorimeters in their lab, they do their arc flash testing, and they take the worst case of wherever that exposure is on the equipment. So, and in this case, and they test all of our equipment, all the configurations that arc block is available in, and that 1.2 was the max. And all of our arc block units will have this UL verified label. So we'll open it up and kind of take a look. So it's isolating your line side and your load side. So MCCs per UL 845, they're already kind of compartmentalized. But with switchboards, UL 891, this is huge now because kind of like it mentioned in that NFPA 70E annex, propagation can make, I would say smaller, you don't want any arc flash event, but propagation can make something on the load side, if it propagates the line in an open construction UL 891 switchboard, it can result in a much bigger, more like catastrophic arc flash event. So arc block is UL verified to isolate your line and your load side. So you won't have that propagation. So it is just protecting your line side. Codes like 240.87 with requirements on the load, like an energy reduction maintenance switch. Everyone has some version of that with some acronym, but those still apply, and we say use it in conjunction for the load side. But arc block is protecting your line side. Arc block is preventing the likelihood of an event, which is key, and it's also reducing the severity if by chance you have one. So it's preventing the likelihood because it is a couple of reasons. It's an enclosed vault, and so your cables going into your lugs are not exposed. So if someone were to drop a wrench, that couldn't inadvertently make contact with your lugs. If they were energized. Also, it's all enclosed, so things like snakes, rodents aren't getting in there. But it's the biggest thing, the way it's preventing is we have these barriers between the phases. So this will kind of explode out. The red material is an insulating and isolating glass, and it's GP03 rated, but it's providing isolation between your phases. So again, the red material, these are barriers, and it's kind of protected and isolated from all sides, like X, Y, Z axis. But these barriers extend from the bottom of the lug down to here is 7 inches. And so for an arc to form inside of this line side vault, an arc would have to travel down 7 inches and back up 7 inches. We've tested it, we've put nicks in the cables, taken off the powder coating of the vault. The only place that an arc is forming is from lug to lug in this case. And so with the barriers at that distance, there's too much impedance. There's too large of a voltage drop from point A to point B. So that's a really, really weak, spindly arc. Plasma physics doesn't allow, like at 480 volts, you can't have longer, an arc can't sustain longer than, I want to say, 2 or 2.5 inches. So here again, it's 14 inches from point A to point B. So that impedance or that voltage drop makes it impossible for an arc to survive longer than a cycle, or 16.6 milliseconds. So it self extinguishes and clears in less than a cycle. And I maybe mentioned on, like in a page before, incident energy is proportional to, your fault clearing time. So because we clear the arc so quickly, the incident energy released is where we get that less than 1.2 calories per centimeter squared. I wish there was we'll have questions at the end. I know I'm throwing out a lot of information. Hopefully this makes sense. So it's not sensing anything. It's not creating a bolted fault. And it's not quenching anything. It's just an arcing fault where the arc self clears. It's totally passive. It's just simply because of the geometry of these barriers make it impossible for an arc to survive longer than a cycle, and it self-extinguishes. It's an arcing fault. It's too weak and spindly and elongated. It can't overcome that impedance, and so it self-clears. And then there is some exhaust, which you saw in the video, and that's to cool the gases below restrike temperature, and that's where we measure the worst case of 1.2 cals. So it's passive. You're not commissioning it. You're not activating a mode. It's not trying to sense something. It's always on because of those barriers and the isolation of your phases. So that's kind of the gist of it. We could do another poll, maybe. Let me actually pause this. It's going to keep playing in the background. We could do another poll after that.
Sure. Should we do poll number 2, Kyle?
Yeah, that's great. Oh yeah, so we'll get to this. But do you see a benefit in the ability to monitor cable connections and ambient air inside of a piece of equipment on a continuous basis to be able to alarm, predict failure rather than an IR scan? So this one maybe is a leading question, but maybe you don't. But do you see value in continuous thermal monitoring of your equipment, basically, where maybe you could set thresholds and alarms if the temperature starts to rise? Maybe you've got a faulty connection that could lead to a larger event. So I think we're good with that, Matt. I can keep going. Perfect. And thank you guys for participating in those. So, okay, so arc block, I'll get into some case studies. We can talk through it. This is a customer case study, large poultry manufacturer. They have a water treatment process, as part of their process in one of their facilities. All they need is a motor control center, but their incident energy after they did the study, at the top there in red, was 146 calories on the line side. So that would blow up an entire enormous facility. PPE ratings don't go above 40 cals. So super dangerous. What they were doing is they were adding an outdoor rated switchboard to their lineup so that they could move their main outside. And then that way the incident energy on their MCC was lower, but that's, more expensive to add that equipment. It's just making install more complex. It's taking up more footprint. And it's not addressing, you still have that 146 cals, it's just moved outside. So we did a study for them. What the study found is we threw out the 3R rated switchboard, which they didn't want or need anyways. And we put arc block before the main inside the MCC. And this brought the line side incident energy down to 1.2 cals per centimeter squared. And then the load side was calculated to be 1.9 cals per centimeter squared. And the reason those are calculated separately, per IEEE 1584, if your main overcurrent protection device is adequately isolated, then you can calculate those separately in the softwares. So you can take into account, in which case they did, the energy reduction maintenance switch that they had in their breaker trip settings. So that's how they got kind of the separate line and load. And then so for the label, your worst case is you'll take your worst case for your label. And so that in this case was the load side, which was 1.9 cals. And that's what goes on the outside of the motor control center. So they brought incident energy significantly down. They were able to reduce their PPE because of that 1.9 rating. They had a simpler and more cost-effective installation by getting rid of that switchboard. So pretty drastic incident energy savings here. Again, here, like there's kind of the two scenarios. They had an adjacent switchboard, all those things I mentioned, additional space, additional labor. It's not really addressing the arc flash versus, hey, add an arc block. You now are isolating the line and load side, which MCC it was, but you're reducing the incident energy. So for me, I think like kind of a no-brainer here. This is just a look at the one line for this. The arc block was here. There was a couple of, there's a transformer feeding that with a fuse that had a really long clearing time. So in this case, it was a service entrance. So arc block is, again, it's passive, it's line side only, so it's not protecting your load. You still need something like energy reduction maintenance switch or whatever else 240.87 requires. But at an instance where you might not have something upstream, or you don't want to trip upstream because it's feeding a whole other bunch of equipment, or it's really far away on a large facility, or your personnel doesn't have access, arc block will bring your line side down to 1.2, and then you could de-energize your load and work on de-energize downstream, knowing that the line side is 1.2 cals. So this kind of shows just a simplified one line, but same kind of scenario. In this case, zone 1 was calculated to be here at 15.6 cals. Zone 2 was calculated to be 1.6, but your label would have to say it would have to be the higher, the 15.6. So if we put an arc block here, now your line side goes to 1.2. Your load stays the same at 1.6. And again, we calculate taking into consideration the breaker and your ERMS because now they're adequately isolated. And so your label would be that worst case 1.6 cals. So same scenario, just slightly different lineup. One thing to note, so the outsides of your labels or the outside of the gear would have that 1.6. We do, like our studies team does say put that 15.6 so that initial label on the front of the arc block to say like, hey, if you remove this cover, basically making arc block like null and void, then yes, like inside of here there is 15.6 cals. But when arc block is assembled, which like there's no reason it shouldn't be, then your labels would be 1.6. But there is that, we do recommend having that second label. If this is taken off, then it's basically what the lineup would be without arc block, if that makes sense. So arc block is available. It's not like a perfect solution right now in that it's it doesn't meet every single solution or scenario, I guess I should say. But where you can use it, it's great. So I'm not saying it's like again, no arc flash mitigation is like a one-stop shop or a fits-all. But we've got it available in our P-frame breaker and our R-frame master pack breaker. So up to 2,500 amps. I would love to have it higher, and that's something we're working on developing. But we've got it available in both our motor control centers and our QED2 switchboards, which you can see here. And then one thing that's really cool, it's available greenfield, or, you know, with a new piece of gear, you can specify arc block and have it come with that MCC or switchboard. Or Schneider Services can retrofill, or when they're modernizing your breaker, they can put it not just in square D gear, but any other manufacturer's gear. If they're modernizing that breaker, they can also put arc block in there. And they come out and they do measurements, and it's, you know, they've got to make sure the bus works. But it can be modernized or retrofitted into anyone's gear, into existing equipment, which is, I think, pretty cool. And obviously, existing installs is a larger base than greenfield sometimes, the new equipment. So what else? We'll get into some of the digital thermal monitoring and things like that. But yep, up to 2,500 amps, MCCs and switchboards, greenfield or existing equipment through services. So, and you can see top right here is that UL verified label that comes on every arc block. And again, so UL verified, you can look on their site and Google it, but it just means they test to their recommended practice a manufacturer's performance claims. That's what UL verified means. And then the gear itself, like arc block in an MCC is UL 845 listed, or arc block in Q82 is UL 891 listed. So it's all got UL, but that verification, Schneider is the first manufacturer to have that UL verified per recommended practice 2986, which I think is pretty neat. So again, just to look at kind of the principles, it's got an arc resistant, like principal shells, meaning overlap joints, the gauge of the thickness where the fasteners are. So you're creating that enclosed, isolated vault, if you will. And then the big thing here, the barriers here, the resin is black as opposed to red, I think is what you saw in the video. But same thing, these barriers are what's isolating your phases from each other. Kind of like a circuit breaker and arc chute design, makes it impossible for an arc to survive in there. And I think I have a picture of how we do the testing. We take seed wire, connect the phases just like you do for arc resistant testing. And that's what self-clears and cools the arc so it extinguishes and is really weak, has that less than 1.2 cals exhaust. So again, just another view of it. Some of this is available like in the e-guides and things like that we've got online. So when the arc when it has an arcing fault and it self extinguishes and clears, your breaker doesn't see that. Again, that's all on the line side. It doesn't trip your breaker. It doesn't affect anything downstream. Your operations won't be disrupted. It clears so quickly, there's not even a temperature rise registered. And I'll show a picture. All you might have is some like some pollution, surface pollution, like some carbon of whatever burned up on your cables. But we've tested some units at our Cedar Rapids lab where the engineers are for this, like 9-10 times. Schneider Legal, being who they are, we're able to claim arc block is good for up to 5 events. If you have a lot of people much smarter than me would argue with arc block, you won't have an event on the line side because of those barriers in your isolated phases. But we're rating it up to 5. And that's another big differentiator between, you know, we're not sensing, you're not commissioning it, it's not a mode, it's not active, it's not a bolted fault that puts more stress on your system. Another difference is this is good for multiple events. It doesn't disrupt your operations, it doesn't need to be replaced, and it's not one and done. So I think that's pretty incredible. But okay, it self-clears. How do I know if there's an event? Is some of the questions we got when we were developing this a few years ago. So this little black box here, I call it like a turkey thermometer. There's a simple like dumb plunger that'll like pressure, that when there's pressure, it'll pop out. This is inside of your section, so you wouldn't see that this is out. But this green, there's a micro switch output contact output on the top. And that would be wired to your universal panel server that comes with arc block And then that could either locally with like a light or something signal go off and just say, hey, you've had an event. You'd want to schedule some maintenance and just go clean up some of that surface pollution, or it could remotely signal something again through that, like through your SCADA or EcoStruxure from the universal panel server to remotely alert you and say, hey, you've had an event, schedule some downtime to check this out. And then to reset it, you just push it back in. So that's the event indication. Another thing, which kind of, it was the reason for the poll, the last one about continuous thermal monitoring. ArcBlock automatically also comes with, or as standard, I guess, with these 4 CL110 ambient sensors. So they do temperature and humidity. They sit at the bottom of, there's heat sinks because it is an enclosed vault. There's not as much airflow, so we use the green extrusions are heat sinks at the larger amperage arc block to dissipate heat from your lugs. And so each sensor, each CL110 sits and reads its corresponding heat sink, which is dissipating heat for its respective phase. Meaning I can get individual readings, relative readings for A, B, C, my neutral, like all of my phases. And these transmit via Zigbee. They have a 15-year battery life. Again, they communicate every 60 seconds. They're sending a reading to that universal panel server. And again, either locally or remotely, you can set thresholds and limits and alarms. So say you have like some corrosion or vibration, something, B phase is starting to wiggle loose, that connection at the lug, and now there's a temperature rise starting. Well, you can set a limit, and hey, if you detect a delta between the phases or a certain rise, I want to get an alarm because that means something's loose, and I want to go check the torques. So you could get an alarm before something happens, and go in and check all your torque settings. So I think this is pretty awesome. The picture on the right doesn't have the cover on it. I should point that out. This was in the lab. ArcBlock has a cover. But it's just showing the heat sinks and the ambient sensors. So now you don't have an expensive IR window where you have to pay someone a lot of money to suit up and take one data point where the next day maybe something comes loose or compromises your connection and you've got a problem, but you don't know because it's going to be another 6 months before you get a scan. So this comes as standard with ArcBlock, and now you're monitoring your lug, like your line side cables coming into your lug, that connection. Just kind of a view at like with EcoStruxure, you can be reading those and getting that continuous thermal reading. Oops. I talked through this a little bit. There's IEEE 1584 that most people associate incident energy with, but there's also, and that assumes an open lineup, and we have a white paper that kind of talks about, okay, there's 1584, but what do you do when your lineup is fully like enclosed and isolated, which ArcBlock is. And so that's where UL 2986 allows us to get verified with that recommended practice to measure the incident energy. So again, you can go online and check this out, read more about it and what UL verified means. And every unit will have this UL label on it with the line side incident energy exposure less than 1.2 cals at the 18 inches. What else? We have a few, so I mentioned the white paper that talks about 1584 versus a fully sealed lineup. That's online. There's also a white paper that came out like 1.5 years ago that goes through how to do the analysis in ETAP, SKN, Easy Power, and how you model that. That's online. And then there's a YouTube recording of ETAP, like live walking you through that. And then I'm fighting with our website people because the link keeps disappearing, but we presented, PCIC is the Petrochem conference. So 2 years ago it was presented in Denver, that 1584 versus fully sealed. And then last fall in New Orleans, they presented another white paper just comparing apples to oranges. Again, it's different applications, different things, but comparing arc resistant versus energy reducing line side isolation, which is, white paper terminology for something like arc block. So those are on there. We've got a couple of blogs. There's additional resources is what I'm trying to say. If you want to dig into this more, they're available, and hopefully we can share them. So again, applications where this is useful: service entrance, unit substation entrance, where your utility might be feeding your gear and you can't trip something upstream, or you don't have access or something like that. So we could probably do the next, we can do the next poll, and then probably get to Q&A as well a little bit early. What are you doing today to protect line side? Example, at a service entrance or a unit substation. So we'll give this just a second. So a lot of you say, we're not doing anything on the line side, but the work is being done downstream. Some, like that case study that I presented at the beginning, are saying moving the main breaker outside of the equipment, so to another location. And then a couple said, something else, something different. So we can, Matt, if we want, we can throw in the last poll, or we can jump to Q&A, totally up to you. Last one. What is the most common main breaker service entrance amperage that you would require in line side isolation? So again, I mentioned we're available at 1200 and 2500 amps. I don't want to lead you guys, but I think there is probably a need for higher amperage at like a service entrance or unit substation entrance, but I'm curious to see what you guys are seeing. Like, where is that cutoff? Hey, I need up to 3000 and then this would be great. Or I need 4 and above. And the arc block, while you guys are answering this, it's available in NEMA 1, NEMA 1A gasketed, and also something that's new at the beginning of this year, NEMA 3R in our switchboards, which is great. So here, the answers here are pretty split between kind of all of the options. So I think it just probably depends on, what you guys are working on. So I appreciate it.
Thank you, Kyle.
Thank you, Kyle. So we got some questions in the chat.
Yeah.
I'll go in order. If the arc block damage from the arcs, how can you monitor it has failed?
Sure. Let me jump. So we say, like, when that event detect, if you were to have an event, if somehow something caused an arc around 7 inches down, back up, that indicator would go off. And there's in like the manual, it talks about basically it's the same type of maintenance. There's no extra maintenance that's required as like annual, just like regular equipment maintenance. The manual articulates it better than that. But this dark that you see, so this picture on the bottom right is after 5 events. So we had 5 arc flash events, and you can see, again, because it clears so quickly, there's not even a temperature rise registered. The rope is still intact that's holding the cables, and you can see just the pollution. So you would go in and inspect, and if for some reason something was wrong, like, yes, it would need to be replaced. But again, we've tested units 9-10 times. Our like warranty claim is 5 events. But if that's happening, something much bigger is going on. But just like a quencher, like quenchers, you've got to replace after 1 time and you have downtime. Relays, same thing. Arc resistant, your whole gear is toast. So the fact that this is good for multiple events, I think is, a pretty awesome differentiator and allows you to have that uptime. I don't know, hopefully that answers that. But you should inspect, like if that indicator goes off, you should go in and do the inspection. But our claim is 5 events.
Thanks a bunch. What is the trade-off of implementing arc block? Quicker breaker trip? Question mark.
No, so it's not. It doesn't really have anything to do with the breaker. You still need a full coordination study, but it's isolated. It's upstream from the breaker. Trade-offs. It's not like, right, I'd say some downsides, it's still limited. We stop at 2,500 amps today. It's fixed breakers only, so we don't have draw out yet. So those would be maybe like the trade-offs. Cost-wise, you'd have to talk to Tom in sales, but it's a much more cost-effective solution than like commissioning a relay or doing a virtual main or having a quencher. So cost certainly isn't a trade-off. Maybe it takes up some footprint in that main section. I mean, it does a bit, but it's not anything massive. In one of those white papers, we have like a cost comparison, kind of where's the trade-off if you've got a main breaker. If you don't have a main breaker, then you would have to add a main breaker, so that could be a trade-off. But we've got some graphs that show like kind of where you reach cost parity compared to something like arc resistant.
Thank you. Is the arc block bottom entry only?
We have in our P-frame option, it's both bottom and top. In the R-frame, right now we just have bottom, but that's something like we're working on developing is the top as well. So lower amperage, 1,200 amps, we can do top or bottom. It just gets like flipped, basically. There's more to it than that, but just bottom for switchboards for the 2,500 amp.
Thank you. Does the retrofit solution require new UL labeling?
If you needed, just like if you were modernizing like another manufacturer's breaker, I should let someone on services, we might need to follow up on this. But I think, yes, if you wanted to get a UL like field inspection done to maintain that, I think you would have to do that. But maybe Tom, you can help me follow up on that.
A couple more. I could be wrong, but I was told the Energy Reduction Maintenance System switch, ERMS, is to be turned on when performing maintenance activities to minimize arc flash incident energy. Should the ERMS be turned on or off during normal operations?
So, I mean, this is a little bit different than what I've been talking about, but yeah, ERMS is a mode with a switch that when you're doing maintenance, so Schneider says like don't do any energized work maintenance, everything should be off, but ERMS it's energy reduction maintenance switch. So when you are doing it, you can switch that into the mode, but during operation, no, you wouldn't have that on.
A couple more. It says zone interlocking will affecting for arc flash events. Will zone interlocking affect for, yeah. Zone interlocking will affecting for arc flash events.
This one we might need to, oops, I'm going the wrong way. We might need to take offline, but yeah, zone interlocking or ZSI is another option. It's part of that whole kind of like arc flash mitigation soup page that I showed at the beginning, but that's certainly an option.
Are the heat sinks isolated from the voltage on the
Yes.
lugs?
Yeah, let me go all the way. Yeah, definitely. And we call it TIMs, TIM, thermal interface modules. I'll show you guys a picture. So this is like an exploded view. Actually, you can see the TIM at the bottom on the tablecloth here. So here's your lugs, you'd have your cables. We want to dissipate heat to the heat sinks, but we need to make sure that they're not live. And so it's kind of like a sandwich of like conducting metal, isolating, insulating material, that same GP03 rated, and then conducting again to the heat sink. So that TIM, once you have your cables in, it goes on, and then your heat sink goes on top of it, and that creates, we can call it like an insulation sandwich. I think I'll find a picture, but I can take the next question too. don't know which way I'm going.
Yeah, Kyle, will you be able to share the presentation for us to share with the attendees?
Yes, yeah, I can. Yeah. I think that's probably the best picture that I have of the Tim. Are there other questions?
Not at this point. I think we've gone
Okay.
through most of them. All
Okay.
of them. Oh, Steve got me.
Yeah, is there a guidance video for implementing ArcBlock on the ETAP and SKM PTW? Is this equipment able to be evaluated in SKM?
Yeah, the white paper covers SKM, ETAP, Easy Power. And I can share the link, but it's online now. So that walks you through that analysis in those softwares.
Another question came up in chat. Is the barrier for the ArcBlock 2500 also 7 inches deep?
Is the barrier? I know. Oh yeah, both both the P frame 1200 as well as the R frame, that barrier extends 7 inches. So then the arc would have to travel down and around that.
All right, dare I say, that's all of the questions we have out there. Well, first off, Kyle, thank you very much for a really informative presentation. I think that there's still going to be questions after your presentation, and we'll be happy to share with everyone not only the presentation once Kyle sends it to us. You'll have a recording of this presentation, and we'll provide Tom O'Neill's contact information in case you have more specific questions for your particular project. So with that, thank you all again for joining us. We appreciate you taking the time. Kyle, again, thank you so much for your time and sharing your expertise.
Thank you.
All right,
Thanks,
everyone.
everyone.
Thank you. Thanks, Matt. Thank you. Have a great day.
See ya. You too.